Good morning, everybody. So, today we will continue with specific acid base catalysis, general acid base catalysis and metal ion catalysis. So, in our last lecture we talked about this specific acid base catalysis. We discussed the general mechanisms for this specific acid base catalysis, and also we talked about general acid base catalysis. We tried to distinguish between them, that under what condition or under what conditions maybe general acid base catalysis gets converted to specific acid base catalysis. So, as I told you that for specific acid base catalysis it has got two types of mechanism. One is unimolecular, the other one is bimolecular, and for your general acid base catalysis it is a combination, that is the your observed rate constant is nothing but a combination of the contributions from your various catalyst. It may be H2 plus, it may be your H2O, it may be HA, or it may be B minus. So, it is a summation of all the constituents, constituent catalyst responsible for your observed rate. Okay. And also when acid concentration or your OH minus concentration is large, then contribution from the other components become negligibly small, and therefore the kinetics resemble specific acid base catalysis. But in general, general acid base catalysis usually occurs in the vicinity of neutral pH. So, general acid base catalysis for enzymes. Now, enzymes often use general acid or general base catalysis. Okay. And within our body the pH is optimum, the pH of physiological pH is around 7, that is 7.4. So, around 7.4 or around 7. So, it is the best region for the general acid base catalysis to take place. Okay. Best condition, pH condition. Now, this enzymes work at neutral pH. So, low H plus or low OH minus concentration. Okay. High effective concentration of general acid or base. Okay, since H plus and OH minus these are low. So, effectively concentration of other general acids or general bases are effectively high. For your enzymes, what is happening, that correct orientation of acidic or basic group around the substrate. Okay. Since the acidic or basic groups of the enzyme that are responsible for a specific reaction to take place, that is the if your mechanism requires that certain groupings must be there, maybe basic group, maybe acidic group, they should be oriented in a specific fashion, so that the reaction will have the best yield. Okay, or the reaction will be very effectively carried out, or it will proceed efficiently. And optimum catalysis at pH 7 around pK. Okay, at pH around pK. So, since it is around pK, we are around pK. So, catalysis will be optimum. That is if your pH is, I mean pH of your medium is very close to pK of the acidic or basic group, then what will happen that it will be the optimized condition for your catalysis to take place. It is not necessarily 7, but you know, if certain groups are having, you know, pK which is close to the pH of the medium, then you know, catalysis will be optimum, because those groups are involved in proton transferring or maybe proton snatching. So, that is why pH around pK is a very important point to think of. Now, amino acid residues having pK close to neutral pH, that is close to neutral pH means pH 7, are able to act as general acid or general base catalysts. Okay. As for example, let us have this an example of a general acid base catalysis, that is carboxypeptidase. Okay. So, here you see that it has got the zinc 2 plus, okay, and your it basically peptidase. So, peptide bond you know, breaking. So, zinc plays role of an acid, that is the fourth ligand is normally H2O, okay, but it is displaced by peptide bond. Okay, that is this peptide is binding. Okay, so water initially was there, that is the fourth ligating position, and the moment it is, you know, this your peptide is coming inside the pocket, then it is displaced. Okay, there is one arginine 145 which makes, you know, bond with, you know, with this arginine plus and this CO minus, there is a there is an interaction, there is tyrosine OH, there is a hydrogen bond formation. Okay. So, tyrosine plays role as second acid catalyst, and this is the key as it holds the molecule in place. So, it is the one which holds the molecule. Okay. There is another arginine over here, and glutamic acid residue, that is you see it is acting as a base catalyst to polarize the water and form the nucleophile. So, you know, it is acting as the base to maybe to snatch this proton, or maybe it is not snatching the proton. What happens that it, you know, this bond is polarized, as a result of which this the nucleophilic strength of this water is increased, so that it attacks over here. Okay. So, you see it is a very complicated phenomenon. It is not only that one molecule, one, you know, molecule like say water is acting here. You see from this side, you know, this one is glutamic acid, you know, side chain, then your zinc. So, zinc, what is happening then, that zinc is you know, polarizing. Okay. So, delta minus of this oxygen has an interaction with zinc 2 plus, so that this bond, you know, I mean this carbon becomes more electron deficient. Okay. So, it is a combined, I mean it is a very combined effect. Okay. And it is an example of general acid base catalyst, that you see here this water is taking part. Okay. Then glutamic acid is also taking part. Okay. So, not only one molecule or one, you know, catalyst, but it is a number, it is a combination of like sum over Ki into concentration of H3O, I mean K H3O plus, then concentration of K, I mean K HA, concentration of HA, like that. Okay. So, it means your observed rate constant is a combination of, you know, various factors, I mean various contributions from maybe H2 plus, maybe from HA, maybe from water, and so on. Okay. So, general acid base catalysis example is ester hydrolysis. You see another case. simple chemical reaction that this H plus, this is polarized, then this bond is polarized, and then this protonation, then water attacks, then this one is formed, this intermediate is formed, then this bond pair is backfired, and so that this bond is cleaved. Okay. So, minus H plus and followed by your product. So, you see that H plus as also water, these two are taking part. So, it is happening maybe it is a case of general acid base catalysis. Okay. So, water as also H plus is involved. So, it is not a specific acid base catalyst, it is a general acid base catalyst, like you see like carboxypeptidase. Okay. Next, ester hydrolysis general option, that maybe it is your enzyme. Okay. And this is your C3COOR. Okay. This is your lysine, then NH2. So, this one NH2 plus, so it makes a bond with your CO carbonyl of your ester. Okay. So, and then reaction takes place. So, you see here this CH3COOR. So, you see that there is one, okay, there is one this H, there is another H with delta plus, this is also with delta plus, and this is delta minus. So, there is electrostatic interaction, because this bonding may be far. So, far for hydrogen bonding. So, in that case, since this oxygen and this hydrogen, they are not in hydrogen bonding distances. So, maybe electrostatic interaction will bind this, or will attract this molecule inside the pocket. So, electrostatic interaction are much stronger in organic solvents than in water due to dielectric constant. Okay. And interior of the enzyme, you see interior of the enzyme. Okay. And the interior of the enzyme, it is generally, in most of the cases, it is hydrophobic in nature. Okay. Or maybe it is, its polarity is less than water, and its dielectric constant are similar to hexane or maybe chloroform in certain cases. So, you see that it is the electrostatic Q1 Q2 by R. So, electrostatic energy. Okay. So, electrostatic energy when it is the dielectric constant. So, when dielectric constant is less, so interaction energy is more. So, interaction energy is more means more of tight binding, more tight binding, that is the tighter interaction. So, tighter interaction means because of hydrogen bond, I mean because of electrostatic interaction, and since the dielectric constant is less, therefore, it is tightly bound, and then reaction will take place. Okay. Like inside, why inside is enzyme of the interior of enzyme enzymes have dielectric constant similar to hexane or chloroform, because it is hydrophobic. You can imagine like it is like a micelle. Inside of the normal micelle is like hexane kind of thing, and outside is covered by water. Okay. So, as if your molecule is micellized, or as if means it is very similar to your micelle. So, as if your ester is micellized within your catalyst, within your enzyme. Okay. So, let us look into the prototropic groups that are present. Okay. N-terminus amino acid, N-terminus, it is alpha NH3, basic form is alpha NH2, and pK is around 7.8. C-terminus, it is alpha COH, and it is basic group is alpha CO minus, it is 3.8. Aspartic acid, it is around beta COH, it is around 4.4. Glutamic acid, it is around 4.6. okay, glutamic acid acidic group, and this is basic group. Histidine, imidazolium ion and imidazole, it is around 7. Okay. Cysteine SH to S minus, it is around 8.7. Tyrosine means it is C6H4OH, C6H4O minus, it is 9.6. Lysine, it is C6H4OH and C6H4O minus, it is 9. Sorry, it is lysine, it is epsilon NH3 plus and epsilon NH2, it is 10.4. Serine, beta OH and beta O minus, it is 13. Threonine, it is 13 also. Arginine, it is 12.5. Peptide bond, it is 14.8. Okay. And you see histidine has got very similar to 7. Okay. So, and also importantly, it is not only that these are some standard value, these numbers may change depending on the environment. That is, pK value is strongly influenced by the environment, that is the environment in which these groupings are there. As for example, in enzymes, the pK of lysine can drop to 7. Okay. So, you see lysine is 10.4, it may drop to 7 depending on which groupings are there. Okay. As for example, suppose if this NH3, that is this extra proton, is stabilized, that is if this charge is stabilized or this proton is stabilized by hydrogen bond, or maybe if this charge is stabilized by nearby some negative groupings, then maybe this one will be stabler. So, these numbers will be changing. Okay. So, so it is very much environment dependent. Environment means whether there is a chance of hydrogen bond formation or whether there is additional charges. Additional charges means maybe positive charge, maybe negative charge. Okay. So, whether that is going to stabilize out of these two, maybe one form, or destabilize the other form. So, these are important or essential things that may be considered. Okay. Okay. Next, move on to metal ion catalysis. Okay. Role of metals in catalysis. A superacid comparable to H plus, okay, but it is stronger. As template, metal ions are able to, so these metal ions can be called as a superacid which is comparable to H plus, but it is stronger. Okay. A metal ion as template, metal ions are able to coordinate to more than 2 ligands and can thereby bring molecules together. So, which is very important, that is proximity is very important. Suppose you want to bring 2 molecules together. Okay. So, that is important. So, if an entity has got option to bind, I mean maybe by electrostatic interaction or maybe by hydrogen bond or whatever, okay, it has got the option to bind 2 entities, then these 2 entities come close to each other for a facile reaction. So, that is why metal ions are able to coordinate to more than 2 ligands and can thereby bring molecules together. Okay. As redox catalyst, these metal ions can be redox catalyst as well. Many metal ions can accept or donate electrons by changing their redox state. So, it is not only doing like binding something, but after binding maybe the metal ion in between can accept 1 electron or maybe can donate 1 electron to this entity. So, what is happening that this metal ion itself can act as redox entity, I mean redox couple, that is maybe after getting 1 electron it may get reduced, or maybe giving 1 electron to another entity it can get oxidized. Okay. Now, what are the features of superacid catalysis? Features are like introduces positive charge into the substrate, making it more susceptible towards nucleophilic attack. So, suppose you have got an entity, and suppose if this metal ion suppose M plus. So, if it binds to this, means as a whole this entity becomes more positively charged. So, another nucleophile having electrons will have better option for this, better option to attack this. Okay. So, that is why it is told that it introduces positive charge into the substrate. So, after binding, the whole thing becomes a substrate, and thereby making it more susceptible towards nucleophilic attack. And also exchange of metal ions is fast, like 10 to the power 5 to 10 to the power 9 per second, but it is slower than the exchange of H plus, because it is the lightest and it is the smallest one, and its exchange, that is exchange of H plus is that, so it is very fast than compared to your metal ions, but it is not that bad, this exchange is not, exchange rate is not that bad. You see, it is 10 to the power 5 to 10 to the power 9 per second, depending on the environment, depending on the metal ion concerned. But although it is a little slower, maybe 10 to the power 9 is 100 times slower, but still since hydrogen plus is lightest, so it has always got the option to exchange very fast. Okay. Metal ion catalysis for biological cases, almost 35% of all enzymes use metal ions for catalytic activity. Okay. So, one third of almost one third of the total enzyme populations use catalytic activity with metal ions. Now, main varieties are like metalloenzymes have tightly bound metal ions. Most commonly are the transition metal ions such as Fe2 plus, Fe3 plus, Cu2 plus, zinc 2 plus, Mn 2 plus, maybe cobalt 2 plus, cobalt 3 plus. Okay. So, tightly bound metal ions. Okay, metalloenzymes are having tightly bound metal ions. And another one is metal activated enzymes. Okay. These have loosely bound metal ions, okay, from solutions, usually alkali or alkaline earth metals like sodium plus, K plus or calcium 2 plus. So, this metal activated or metal ion activated enzymes loosely bind metal ions from solutions, and these metal ions are sodium plus, potassium plus, calcium 2 plus. Okay. So, these are, second category is metal ion activated enzymes, and the first category is metalloenzymes, that is having tightly bound, firmly bound metal ions within. Okay. Metal ion catalysis, 3 ways for catalysis. Okay. Binding to substrate to orient them properly for reaction. So, first one is 3 ways, means out of the three ways, one is the binding to substrates to orient them properly for reaction. Second one is mediating oxidation reduction reactions through reversible changes in metal ion oxidation state. Third is electrostatically stabilizing or shielding negative charges. Okay. So, that means for metal ion catalysis, the first one is the binding to substrates to orient them properly for reaction. Okay. So, metal ion will bind to the substrate so that the substrate is properly oriented for the reaction to take place. Next is, it is mediating oxidation reduction reaction through reversible changes in metal ion oxidation state. So, that means maybe it is the mediator. Suppose if it is a redox reaction, then the metal ion is acting as your mediator. Okay. So, that means maybe you have got, suppose you have got metal ion over here, you have got one entity over here, another entity over here. So, what is it is doing is, maybe it is accepting one electron and maybe it is giving this electron over here. So, first step it is reduction, second step oxidation. So, reversibly it is switching from say maybe M plus to M plus plus to M plus, then to M plus plus. So, it is a reversible process. Okay. So, reversibly it is doing like this. And so, mediating oxidation reduction reactions through reversible changes in metal ion oxidation states. Third one is electrostatically stabilizing or shielding the negative charges, because it has got positive charges. So, electrostatically it is shielding the or stabilizing the negative charges. Let us have one example, metal ion catalysis in carbon-carbon bond cleavage. Decarboxylation of oxalosuccinate by isocitrate dehydrogenase. Okay. So, it has got the Mn2 plus and this is the enzyme part. So, Mn2 plus binds over here, I mean makes a bond, and then through this mechanism this backfires and then this bond form breaks, and ultimately decarboxylation occurs. So, you see that this is minus CO2. So, this one will be will be going, I mean no, not this one will be going, this carbon dioxide will be going out. So, this one is here and then it is given, this bond pair is given to here. So, you see that this stabilizes this negative charges, Mn2 plus stabilizes this negative charge, and what happens that since it is polarized because of this 2 plus, this carbon becomes electron deficient because this oxygen has an interaction with Mn2 plus. So, therefore, there is always an inward pull, so that it helps this decarboxylation. So, then it comes out, this carbon dioxide comes out and then it backfires, and then with a proton it makes a bond, so that this double bond becomes single bond, and then finally this goes out. So, Mn2 plus accept the developing negative charge. So, this developing negative charge means it is backfiring. So, as if these electrons are pushed from this region to this region. So, there is a developing negative charge. So, this one is accepting that developing negative charge. So, it is acting as Mn2 plus is acting as if it is a sink for electron. Okay. M3 plus like L3 plus are also good, M plus like Na plus, K plus and H plus are much less effective. Okay. Other possible substrates like this one, similar substrates where Mn2 plus is acting as electron sink. So, both CO minus and CO are required for correct binding of Mn2 plus. So, this COO minus and CO, these two are required. You see, this is COO minus and CO, this is COO minus and CO. Okay. So, oxaloacetic acetic acid and this 3-keto glutaric acid, these are also possible substrates. And cleaving, the requirement is cleaving CO minus group at the beta position. Okay. So, this is your alpha position, this is beta position. So, this one is beta is cleaved. So, these are the requirements for Mn2 plus to act as metal catalysis, metal ion catalysis in CC bond cleavage. Okay. Metal ion catalysis in additions to CO or CN bonds. Okay. So, in that case copper 2 plus, you see copper ions are effective catalyst for hydrolysis of alpha amino acid esters. You see copper 2 plus does this binding, I mean bond formation, then OH minus attacks over here, because now this bond is polarized. So, it attacks over here, and then there is a 5 membered intermediate, then H plus is in presence of H plus, this one is taken out. So, hydrolysis product is formed. Okay. So, CH3OH is released. So, hydrolysis product is formed. So, these are less effective in hydrolysis of amides because of tighter bond between metal and the substrate, because it is the ground state stabilization. So, for your uncatalyzed reaction, the uncatalyzed reaction, it requires more energy, but your catalyzed reaction for your ester, this ester, or maybe for your amide. Okay. Now, for your amide, it is this is less effective, because because tighter bond between metal and the substrate. But anyway, it is effective in this reaction, hydrolysis product, because CO or CN bond, this is metal and catalysis in addition to CO, because you see here it is basically an addition reaction to CO. Okay. First addition of OH minus, okay, and then maybe because of the presence of H plus, it is dissociated, but basically metal ion, in presence of metal ion, this addition reaction occurs. Next, metal ion catalysis in hydrolysis of phosphate ester and anhydrosis. Hydrolysis of phosphate esters, as for example acetyl phosphate or anhydrides like ATP, okay, is always catalyzed by metal ions, usually Mg2 plus. You see, this is the scheme, that Mg2 plus makes a bond between this one and that one. Okay. Like the other case I talked about, it is in one case it is keto, another case it is carboxylate, here it is phosphate. So, bond formation and then subsequent reactions will give rise to H2PO4 and CH3COO minus in presence of Mg2 plus. So, now here what is the role of metal ion, that is Mg2 plus. So, it is effective for neutralization of negative charge in the substrate, this negative charge, because this has got 2 negative charges and it is 2 plus. So, negative charges in the substrate is neutralized to enable the approach of the nucleophile, okay. Because it is neutralized now, a nucleophile can approach, and stabilization of the leaving group, neutralization of charge. So, this is your stable leaving group, this is your leaving group. So, their charges are also neutralized, in presence of water, they form these two. So, leaving group stabilization, I mean is also important over here. For your ATP, see it is Mg2 plus, adenosine triphosphate, Mg2 plus, making bond like this, the similar disposition you see. This keto group phosphate, this is also, although this is a PO and phosphate, then this bond is cleaved, this bond is cleaved, and then in presence of water it produces H2PO4 minus. Ester hydrolysis again in enzyme. This is a zinc containing enzyme, this is your CH3COO R. So, in presence of zinc, this bond is polarized. So, water now can attack, because it is properly oriented and water now can attack. So, that is it becomes a tetrahedral intermediate, and then this developing O minus, I mean negative charge backfires, and then this bond is cleaved. Okay. This proton is taken up by this one. So, this bond is cleaved. Okay. So, metal ions when bound to protein, prosthetic group or cofactors can also help in catalysis. In this case, zinc is acting as Lewis acid, okay, zinc 2 plus. So, this lone pair is donated. So, it is acting as a Lewis acid. Okay. So, so therefore, this bond is polarized. Okay. So, it coordinates to the non-bonding electrons of the carbonyl and inducing charge separation. So, it is polarized and making the carbon more electrophile. So, this carbon is more electrophile or more susceptible to nucleophilic attack. So, nucleophilic attack means this water is a nucleophile, so it attacks. So, basically this bond is polarized in presence of zinc 2 plus. Okay. So, metal ions do such thing. Metal ion catalysis, ester hydrolysis, another case that this bound water with zinc. Okay. This is your ester inside the pocket. So, this one, this lone pair, this proton is eliminated. Okay. So, here initially zinc 2 plus is bound to water, okay, is acting as a Lewis acid. So, therefore, is bound water and then this proton is removed from here. So, therefore, it is ZnOH kind of thing, and then this lone pair of ZnOH attacks this one, and thereby this hydrolysis is taking place. So, metal ion can make potential nucleophiles also over here. In earlier case, electrophilicity of this carbon is increased, but here the nucleophilicity of your water in the form of OH is increased. Okay. And therefore, so what happens that when coordinated zinc is present, then it is acting as a good attacking agent. So, its electron pair is attacking over here, and therefore, and then thereby your hydrolysis is occurring. Okay. For example, when pK of water, for example, the pK of water drops from 15.7 to 6 to 7 when it is coordinated to zinc or cobalt, the hydroxide ion is 4 orders of magnitude more nucleophile than water. Okay. So, because of this hydroxide ion formation, so it is highly nucleophilic than water, because it has got high charge density, negative charge density on oxygen. So, therefore, it will act as a good nucleophile compared to water, of course. Now, covalent catalysis, what is covalent catalysis? It has got 3 stages: the nucleophilic reaction between catalyst and the substrate to form a covalent bond. Okay. The withdrawal of electron from reaction center by the new electrophilic catalyst, and the third one is the elimination of catalyst, that is the opposite of 1. Okay. And nucleophilic catalysis, the covalent bond formation in the rate determining step, electrophilic catalysis, withdrawal of electrons in the rate determining state. Okay. Now, you see, so there are 3 stages. The first stage is the nucleophilic reaction between catalyst and the substrate to form a covalent bond. So, there is a covalent bond formation. Okay. Catalyst and the substrate, there is a covalent bond formation. Then withdrawal of electron from the reaction center by the new electrophilic catalyst, okay, and then elimination. So, these are the 3 stages that we need to consider. Now, nucleophilicity is related to basicity, but not exactly same thing, but they are really somewhat related. Instead of abstracting the proton, nucleophilically it attacks and make covalent bond. Okay. So, basicity has got relation to proton abstraction, and nucleophilicity has got some connection to covalent bond formation. Okay. So, good covalent catalysts must have high nucleophilicity and ability to form a good leaving group. Okay. For good covalent catalysis, you need to have high nucleophilic catalyst. Okay. Also, polarized groups like easily distortable electron cloud are good covalent catalysts like imidazole, thiols, etc., like lysine, histidine, cysteine, aspartic acid, serine. Coenzymes like thiamine pyrophosphate, pyridoxal phosphate, these are also good covalent catalysts. So, in this case nucleophilicity is more important. So, and also polarization, I mean polarized groups are very important, and leaving character, leaving group character is also very important while considering covalent catalysis, that is for effective covalent catalysis. Now, an example covalent catalysis, acetoacetate decarboxylase, biacetoacetate decarboxylase, covalent catalysis biacetoacetate decarboxylase. You see, it has got lysine and NH3 plus. So, this is your acetoacetate. So, what is the product? Product is CH3COCH3 acetone, and then it is your carbon dioxide. So, what are the steps? Steps is basically when water is eliminated. Water is eliminated means this reacts with this one, this carbonyl one, not this one. This carboxylate one will not form any such bond, because this is resonance stabilized. Okay, this is resonance stabilized, and generally this one makes bond with this one. Okay, and these are very stable. This COO minus is very stable, so therefore it will not react with this one. So, only this one will react with this one. So, what happens that this CO and this NH3 plus. So, one molecule of water is eliminated in this equilibrium scheme. So, it attaches with this NH3 plus, then double bond, then this one. Then this one backfires. Why this one is backfiring? Because this is N plus. So, this one has got tendency. So, there is an outward pull of this electron, I mean pull of this electron cloud this way, because this is N plus. So, it is electronegative as also plus charge. So, this bond is polarized this way. So, that is why easily distortable electron cloud. So, what is happening that when this backfires, there is a pull, there is a pool of electron, I mean from this side to this side. So, this backfires, then this bond cleaves. Okay, this bond cleaves. So, minus CO2. So, this is your product. Okay, and then you see there is another side group, maybe BH plus, I mean BH. So, this BH proton is snatched by this CH2. Okay. So, this backfires, okay, and then this one, this C snatches this proton from here, thereby making B minus and this one, and then in presence of water hydrolysis will take place. Okay, hydrolysis will take place to give rise to your product. So, what happens is that there is a covalent bond formation first, as I told you that that the nucleophilic the nucleophilic reaction between the catalyst and the substrate to form a covalent bond, then withdrawal of electron from the reaction center by the new electrophilic catalyst. You see the covalent bond formation, then withdrawal of electron, okay, and thereby this bond is cleaved. Okay. So, initially this bond formation, covalent bond formation, then because of this N plus, this electron cloud is polarized this way, therefore, there is a outward pool of electron. So, therefore, this carbon is partly electron deficient. So, to satisfy the electron deficiency, there is a tendency that this bond, maybe if this bond is switched from here to here, so its electron deficiency may be somehow satisfied. Therefore, this bond cleaves and carbon dioxide is released, and following this scheme, the reaction, following this scheme, your product is formed, that is CH3COCH3, okay, along with carbon dioxide. So, this is the schematic of covalent catalysis, where acetoacetate decarboxylase is the enzyme which decarboxylases, where decarboxylation occurs from acetoacetate. Now, covalent catalysis, so rate acceleration through transient formation of catalyst substrate covalent bond formation. So, this covalent bond formation, thereby reaction rate is accelerated. Decarboxylation of acetoacetate by primary amines. Amine makes nucleophilic attack to carbonyl group of acetoacetate to form ship base, that is imine bond. Okay. So, this is what is happening, this is in ship base formation basically, okay, imine formation, and then as I have shown to you how this reaction proceeds. Summary for superacid catalysis. Okay. Polarization of bonds, especially CO, accepting negative charge, that is the electron sink, neutralization of negative charge in the substrate to facilitate the approach of the nucleophile, and stabilization of leaving group, reduction of charge. Okay. So, these are the summary for your superacid catalysis, as I already have told you, metal ion catalysis. Okay. Okay, polarization of bond, then accepting negative charge, neutralization of negative charge in the substrate to facilitate the approach of nucleophile, and then stabilization of the leaving group. So, these are the points that we should think of. Next is metal ion as template in surface epoxidation. You can maybe have a look at, it is a mechanism proposed by E.J. Kure. Next is advantages of metal ions over H plus. Why are we looking for metal ion catalysis? Okay, let us go back, let us try to recap this metal ion catalysis. Okay, another example is your Mn. Okay, here it is your Mg2 plus. So, what is the need of or what is the importance of this metal ion catalysis? Okay, what is the advantage? Now, metal ions have higher charge. Higher charge means it is either it is M2 plus or M3 plus, maybe Cu2 plus, maybe in some cases it is Mn2 plus or maybe Mg2 plus. Okay. These work in the neutral pH range. Okay. So, this is very important for enzymatic reaction, since our physiological pH is around 7. So, it is the neutral pH. So, that means the catalyst which can work effectively in this region are very important. Okay. So, are of importance. So, that is why, since these metal ions are working or can work in neutral pH range, therefore, it is always advantageous rather than H in presence of H plus, because in that case if you have high H plus concentration, then it will be acidic. So, for physiological requirement, acidic pH will not be very much acceptable. Now, it can coordinate with several groups, which is called the template effect, not only a single group, but also with more than one groups. like in one case maybe it is phosphate, another case it is CO, or maybe as I told you that Mn2 plus. Okay. So, Mn2 plus simultaneously binds with this COO minus and also this CO, as I showed to you earlier. Let us go back to it. See, Mn2 plus, it binds with this one as also this one. So, it is called a template effect. So, if this template is present, then it will be effective in doing that one, and also since Mn2 plus is a high charge. So, it tends to stabilize this minus charge along with the would be or incoming negative charge. Because of this decarboxylation, there is a developing negative charge. So, this developing negative charge is stabilized, and only it is possible because if such template is there. So, that is what is called the template effect. Okay. And many metal ions have redox property. So, redox property means it is reversibly accepting electron to get reduced, and then again this accepted electron is transferred to another entity, and thereby it is again oxidized. So, reversibly it is reduced, oxidized, and the cycle is completed. Cycle is completed, that means the process of redox reaction occurs via this metal ion. Okay. So, exploiting this redox property of the metal ions, we can have interesting chemistry. So, what we have learned out of such out of this discussion? Here we have talked about general acid base catalysis, then we moved on to metal ion catalysis. Okay. So, why have we moved on? Because these super acids are very stronger, maybe in some cases it is stronger or maybe comparable to H plus. So, they can be good catalyst. Okay. And they have got these have got very good option for carrying out redox reactions during its binding. That is, this metal ion can accept or donate electrons by changing the redox state. So, exploiting that, maybe we can have something extra, and also these as template metal ions are able to coordinate to more than 2 ligands, and can thereby bring molecules together or bring a specific conformation. Okay. That is very useful for the effective reaction. Suppose we have got 2 groupings are like this. Okay. But when metal ion is coordinating with maybe this group or maybe this group, so maybe conformation becomes like this, that is parallel conformation. Okay. So, what is happening that maybe in this particular conformation, maybe the reaction is more effective, well, that is the rate is faster. So, this template effect is very important, and also we have learned covalent catalysis, which happens via formation of covalent bond, and then eventually withdrawal of electron from the reaction center, followed by elimination of the catalyst, leading to your product formation. Okay. So, this covalent catalysis, then superacid catalysis, then acid base catalysis are very important, not only in chemical reactions, but also in biochemical reactions. Okay. And these catalysis, that is metal ion catalysis, maybe covalent catalysis, can give rise to interesting results, interesting chemistry. Okay. So, with this I conclude for this session, I mean this lecture. Maybe we will take up kinetic isotope effect in chemical reaction in the next lecture. So, till then, thank you.